Thank you everyone for joining. In the tutorial today, we're going to talk about developing schemas and parsers for computational data using NOMAD and this new package that we've been developing, NOMAD Simulations, which is a schema plugin for NOMAD. And right now I'm going to give it first an introduction into the NOMAD software and repository just to get us all on some sort of the same footing. I can see that there's a variety of backgrounds in the participants already. So try to give some people background who aren't as familiar with NOMAD and FAIRmat. So I just want to start by saying, if you don't know, FAIRmat is an NFDI consortium for material science data infrastructure. And our goal is to develop fair data infrastructure for materials data, and this is materials data of all kinds. So today we're going to talk about computational data, but there's similar activities going on for experiments and for synthesis and for applications, which are a combination of these different areas. And we have many participants and collaborators all over Germany and actually quite internationally as well. So that gives you sort of a broader context. And now I want to introduce the computational team. So I'm Joseph Rudzinski. I'm the coordinator of the computational area at FAIRmat. And we have 4 tasks, which are focused on different subdomains of theory and computation. One is ab initio calculations. Our domain expert there is Nathan. Nathan's going to tell you about parser plugins a bit later in the tutorial. So he's the one who takes care of managing and developing the ab initio parsers and the features associated with that. And there's many of these already. If you're familiar with NOMAD, you know that there's a history of lots of development in this area. But we've also expanded to classical simulations and multi-scale modeling, and our domain expert there is Bernadette. And Bernadette will be in the chat to help answer your questions and with discussions. And then we have excitations, and our domain expert is Chema. And Chema is also the lead developer of this schema plugin, so that we're going to mostly focus on today. So he's going to tell you about that in the next section. And then actually Esma, this is a new area, and Esma has not quite joined us yet, but I wanted to mention this area is coming, and she's going to join us soon as a domain expert to sort of broaden the scope in terms of electronic structure calculations, more focused on computational chemistry applications. So the NOMAD software is what we're going to be talking about today, and this is the primary infrastructure software that we're developing within FAIRmat. So you can go to nomad-lab.eu, that's the homepage, and there you can find resources to the repository itself, to the docs and other resources. And I'm going to talk about this on the next slide, but the goal of building or our philosophy of building this NOMAD software is to to develop it in a way according to these FAIR principles. But first, I want to give you an idea of sort of how this works, the basic functionality of the NOMAD software, especially for simulation. So the idea is we run some calculations on our computer or our local HPC resources or such, and then we upload the raw simulation files to NOMAD and to the NOMAD repository, and these raw files are then processed and stored in what we call an archive. And the NOMAD archive is just a structured way to store the data, and it's a way to store the data in a normalized form, right? So that these archives are comparable. This metadata is comparable between simulation files that come from distinct softwares. So that's one of the principles here. And then the archive can then be used to display some visuals and have some search features within the GUI, which I'll tell you more about in a second. And then we can follow a different line to get to these resources. So we can go up here, and there's actually an API. So instead of uploading these sort of by hand or a drag and drop, we can use an API, and we can do this via the terminal or via Python, and this also will reach the repository, and then we can utilize the GUI in this way, and especially the search. And then we have this AI toolkit here, which is essentially a series of notebooks which utilize this API and demonstrate how to perform some machine learning techniques while using the data in the Nomad repository. So that's the basic idea. And as I said, the software is developed according to these FAIR principles, so findable, accessible, interoperable, and reusable. And today, I really want to focus on the interoperable part. So this is where the schema really is important, which helps to define the semantic context of this metadata that we're storing. And this could be within some data schema. This could be also sort of deeper, that's linked to taxonomies or ontologies. And this, of course, is very important for being able to compare data across different groups, different researches, institutes, and also eventually different domains, which I'll mention a little bit later. So now back to the Nomad functionality. Again, I just want to give you a basic flavor, just in case you're not familiar, also of some recent updates. So the basic functionality is that, as I said, we have this repository and there's this GUI associated with it and also API, and we can query the repository in various ways. So in the GUI, there's a search bar and we can search by element, material, method, and there's a whole bunch of options here. And this is continually under development, especially as we expand the scope of Nomad, then this search becomes more and more built out. And also we have apps which are essentially specialized dashboards which for particular domain data. But I'm not going to go into that at the moment. So there's already lots of data on Nomad, and a lot of this data is representing the ab initio calculations, because historically this is where the Nomad started, but we're starting to build up more and more data in other regimes, as I mentioned, these classical simulations, excited states, and so on. So maybe if you've used Nomad in the past, but you haven't been paying attention recently, it'd be interesting to see some of the new features we've developed over the past couple of years. So in the context of ab initio calculations, there's new search functionalities. You can search by precision, so you can fine-tune the details of the input parameters of the calculations that you're searching for example, from K-line densities. You can navigate entries based on self-interaction energy. So there's new filters having to do with DFT plus methods, and you can filter based on some code-specific tiers. So this is talking about the I forgot the word I was going to use, but basically the level of basis sets that you're using in the calculation. And then we also have functionality of to characterize core hole orbitals. This is, of course, stored in the metadata, but there's also visualizations using this system hierarchy toolbar, so you can see which atoms are associated with core hole orbitals in this case, and I'll show you some other applications of this bar in a second. So the other area is that we have, in terms of new features, we have support for molecular dynamics simulations, and this is where this hierarchy of systems comes into play in terms of the visualization of molecular topologies. So for example, this is a protein simulation, and you can click through the different levels of the system, the protein, the water, and then the different subunits of the protein, and you can see very easily what the system is composed of. And then we store and display the standard thermodynamic properties. So these are now trajectory properties that we're storing. So this is a sort of different case of a metadata schema. And then we do some automated calculation of some basic molecular properties like radial distribution functions and mean square displacements. And we have sort of two main parsers for standard simulation packages, GROMACS and LAMMPS, that we develop. And then we're also working on this H5MD NOMAD format, which is essentially a build upon a previous schema to allow you to store simulation data, molecular dynamics simulations from any software according to this schema, and then that is essentially mapped to the the NOMAD schema, which we'll talk about later. So this allows you sort of flexible uploads of molecular dynamics data. And then in the excited states regime, this is having to do a lot with various excited states methods and also support for workflows that are associated with these methods. So here's a list of standard workflows that are now supported. And you can see that for these workflows, there's some visualization features like comparing band structure for the DFT versus the GW part of the workflow. And then there's also the calculation and visualization of spectroscopic properties. And this, again, is inherently linked with these developments of support for workflows. And so, as I mentioned, there's some standard workflows. So I already mentioned GW. These workflows will be automatically recognized by our parsers and then visualized in the overview page of these entries. So for example, here, and also molecular dynamics is another example, also geometry optimizations and such. And these workflow graphs that are that visualize the workflow are interactive. So here is a video showing some of the features, but basically you can go between the filter between the different steps. And this is like a hierarchical workflow graph. So you can click, if you have workflows on top of workflows, you can click inside one workflow and see the sub workflow inside of it. And that sort of comes into play when you build custom workflows. So in addition to these standard workflows, which are automatically identified, you can connect your individual uploads in NOMAD with these custom workflow files. And if we have time, Chema will explain a little bit about that, but we have documentation already. This is the navigation bar of the general NOMAD docs. And if you go under domain-specific examples, there's a computational data section and then workflows, and that's where you can find that. And there's some other information that's sort of computational specific, and we're continuing to work to build this out. Okay, so what's next? Well, we're in the middle of a huge transition with the NOMAD software at the moment, where we're migrating to this plugin-based system. And this plugin-based system will lighten the NOMAD software, so it's easier to sort of use by default. And then it also will make it much easier to sort of build customizations and extensions to NOMAD through these parser and schema plugins. And this schema plugin that I list here, NOMAD Simulations, is the one we're developing right now, and the one which is the focus of this tutorial. So this is a complete refactoring of NOMAD's primary simulation schema. So Chema is going to tell you all about that. And basically, at the end of this development, we're going to move the so if you're familiar with the NOMAD structure, we're going to move the computational data from this run section into the data section. This is where the experimental data lives. And this means that we can now start to think about interoperability between different domains. And in addition to that, as I said, so you can maybe now imagine how you can develop your own schemas and your own parsers. And this is exactly what we're going to talk about today. Finally, there's the ability. So you could use standalone parsing before, but this will be much easier to do standalone parsing, which will essentially allow you to utilize NOMAD and NOMAD, the schema package, with your custom parser for other functionalities. So now to the overview, to the schedule for the tutorial. So as I said, Chema is going to tell you all about this NOMAD simulation schema plugin, the overall structure, and how sort of the conceptual, some tips and conceptual aspects of building up a good schema, a good data schema with these like FAIR principles in mind. And then Nathan's going to tell you a bit about how to build a parser plugin from scratch. I will give some basic examples of extending this NOMAD simulation schemas for custom methods and outputs, and then probably won't have very much time, but we will mention at the end some documentation again for these custom workflows and such. So if you already haven't gotten this link, you can, this should be now pasted. I guess I already put this in the Discord channel. We can also paste it in the chat. So we have these docs, and I'll just show you. So we have this documentation page for the tutorial, and this has information on all the sections. The tutorial is going to be presented mostly through sort of verbal presentations. There will be some hands-on aspects to it, but mostly we're going to give you the fundamentals now in sort of conceptual fundamentals, and then you'll be able to go to these docs later, and we'll continue to build these out over the next couple of days with some more examples and depending on your feedback. And so this should be a useful resource moving forward to really put into practice the things that we talk about today. So really fast, in the last 2 minutes, I just want to mention some other resources. So if any of the features that I mentioned to you today, like earlier, are interesting to you, or if you are a complete newcomer to Nomad, you can look at our previous tutorials, and I linked these slides to the docs, so you can find my slides and you can get these links. So this one's more about molecular dynamics. This is more about electronic structure. So those are good resources. As I said, you can go to the general documentation, so the homepage, learn documentation, and again, there's these domain-specific examples and then computational data. That should help you out. You can also look at the general docs. But really what I would recommend, the main resource for like getting started or answering questions is to just come to Discord. So most of you are already there, which is great. And you can also in the future come to under computational section, come to this general computation, post your questions, interact with us. This is a very large and quickly evolving project. So sometimes it's difficult to navigate all the documentation. So I would really suggest to utilize this resource to just interact with us directly.